hope you're doing well. Josh and I will be revising for your pleasure some sample questions that we've selected from the yellow book. So we opened the back of the yellow book. We thought these are a good smattering of questions which are more or less representative of what you will find on your exam. The exam will be 20 minutes long. Unlike other tests you might have seen where you have 25 minutes, no, this test will be 20 minutes long. Josh, shall we get started?
Sure.
Cool.
I'm here, but I'll be back in a minute.
Yes, awesome. All right, so behold, the first question. This is a 1 mark question, so 1 mark. It asks us to show that a set is not a subspace. And when you see something is worth 1 mark, it should be more or less a matter of writing down one line, getting the mark. It's not, 1 mark tells you this is not a complicated question, don't go crazy with it, don't spend a lot of time on it. 1 mark, get your mark, move on. Show that this is not a subspace. The first thing you should always check for subspaces is, does it contain 0? That is the easiest thing to check. Do that one first, because it's the easiest. And in this case, S does not contain 0. Let's say 0 is not in S. This is nice. You do actually need to say a bit more. This is just telling your reader that you know it's not a subspace, you know 0 is not in it, but you do actually need to demonstrate that 0 is not in it. It's not sufficient to just say, clearly 0 is not in S. No, you need to actually demonstrate somehow that 0 is not in S. 0 is, in this case, 0, 0, which is an element of R2, but, so that's kind of halfway to being in S. S is a set of all things that are in R2 and satisfy the condition. 0, 0 is in R2, but alas, 3 times the first component minus 2 times the second component is equal to 0, which is not equal to 1. That's why 0 is not in S. It doesn't satisfy the second condition. Good, nice easy question to get us warmed up with. Josh?
Yeah, so this is a 1 mark question. It should be quick to answer. Yeah, that's a nice little proof.
Would you accept someone who just says,
because
0 is not in S? How would you feel about that?
Well, I don't feel you missed the show part. You haven't really shown me. You've told me, but I don't feel like you've shown me. So no, I won't accept that. You have to show me why it's not in S.
Yeah, I think there's always something to do here with these showing 0 is an element of the set.
Actually, all the questions we do today will you do need to give reasons. They'll either be a show or they'll explicitly tell you to give reasons.
All right, okay. Next question. There we go.
Okay, now I would need to check, but I believe this is a 3 mark question, or possibly 2 marks. Now, there's an important thing you should do whenever you're dealing with these sort of questions. Whenever you copy down a set of polynomials or a set of vectors, always check the components. And actually, unintentionally, there's a lesson here, because I realized when I copied this down, I copied down the incorrect component here. This was actually supposed to be 1 minus t.
And it is 3 marks.
Yeah, 3 marks. This is a 3 mark question. And I double checked, the rest of them should be correct. It's always good to double check when you copy down information. You want to make sure you're answering the right question. If you're starting with the wrong information, you're not answering the right question. Okay, so the question is, do these polynomials form a spanning set for P2? Well, To show that they form a spanning set, or to check they form a spanning set, all I need to do is show that there are actually three linearly independent vectors, or three independent polynomials here. Because remember, P2 is a three-dimensional vector space. Okay, so let's see. So I want to check the linear independence of these polynomials, so what I'm going to do is, it's always hard to start these questions. I want to, well, let's consider the following. So I'll start down here. So let's consider the equation. So when you're checking linear independence, you want to take a linear combination and check what solutions, what combinations give you 0. So we're going to have a look at the equations given by this. Plus alpha 2 minus t plus 3t squared plus alpha 3 plus 5t plus 5t squared plus alpha 4 t minus 2t squared equal to the 0 polynomial. And if we pull out the coefficients of this, well, then we'll have the set of equations we need to consider. So I'm going to do that all in one step and say, pulling out the coefficients of, well, the powers of x, powers of t, sorry, we get the augmented matrix. So we have to consider the following augmented matrix. So if I'm pulling out the constants, that would correspond to these terms here, I'll have a 1, 2, minus 1, 0. So this is, well, if you read this, it says alpha 1 plus 2 alpha 2 minus alpha 3 must equal, must equal 0, but I'm not going to put on the augmented column because it doesn't contain anything interesting. Let's put out the things which are linear in t. We'll have a minus 1, minus 1, 5, 1. Minus 1, minus 1, 5, 1. And finally the powers of 2, t squared, we get 2, 3, minus 5, minus 2. So if I'm looking at this matrix here, and if I can row reduce this matrix here, it'll give me information about these polynomials. Okay. So let's just do our row reduction. It shouldn't take too long. So a fairly standard step, I want to get rid of this minus 1. So let's take row 2 and make it row 2 and add on row 1. So first row hasn't changed. The second row is now a 0, a minus 1 plus 2 is 1, 5 minus 1 is 4, 1 minus 0 is 1. Let's get rid of this 2. So so take row 3 minus twice row 1. So row 3 is row 3 minus twice row 1. 2 minus 2 is 0. 3 minus 2 is minus 1. Minus 5 plus 2 is minus 3. And this is just a minus 2. I'm going to change that. And only one more row operation is required. Let's do it over here. So row 3 equals row 3 plus, so I'm going to add on this row here, row 2. That gives me a, well, let's see. So these zeros combine to give 0, these sum up to 0, these sum up to 1, and these sum up to minus 1. Alright, so now looking at this, I have enough information to answer the question. I know, I know how many linearly independent vectors there are. So just a reminder, these are leading elements. We have 3 leading columns. So I can draw this information together to answer the question. So, right, so since there are three leading columns, there are three linearly independent vectors, or maybe I should say polynomials. Here. And since you're taking three vectors from a three-dimensional vector space, which are linearly independent, they actually have to be a spanning set. In fact, those three, well, the three corresponding polynomials would be a basis. So let's say, and since, remind ourselves that the dimension of P2 is equal to 3. So you should probably state this to make sure people understand, you know. Let's see. Yeah, well, these must be a spanning set. So I think that does answer the question, but I'm welcome to see what criticism I'm going to get. So you have three linearly independent polynomials, and because they live inside a three-dimensional vector space, that means they must be a spanning set. So, comments?
Cool. Yeah. So what this is saying is that just these three alone are enough to span P2. And therefore, the span of those things must be P2.
Yes.
Cool. And I like that you kind of use the linear independence to get there, because if you have three vectors in a three-dimensional space, then linear independence and spanning are the same thing. So, and linear independence is kind of nicer and easier to show. So, using the fact that three vectors in R3 must be linearly independent precisely when they are a spanning set for P3, we're able to see that this is a spanning set for P3.
Yeah. I guess I could state that these three do form a basis, and if you have a basis, well, then you definitely have a spanning set.
Yeah, you've got a lot more machinery at your disposal when you have the kind of three vectors in a three-dimensional space that are. Yeah, then there's kind of theorems you could use to show it's a spanning set. A kind of more vanilla way of answering this question would be to take an arbitrary polynomial from P2, maybe with an a plus bt plus ct squared, and show that that's always there's always a solution to that, and that's the kind of thing that you could do. It's a little bit more fiddly with the algebra, I think, but it's definitely shows that it's in the spanning set in a fairly mechanical way. So there's merit in both of these methods. I kind of like this method. It's a bit fancier, but you can just go to the straight out vanilla method. Show an arbitrary polynomial is in the span of these things by row reduction. Yeah. One minor thing. I do like putting the row of zeros there.
Okay.
That's just me, because it's literally kind of a more literal kind of expression of that equation with the zeros on the end.
Okay.
Anyway.
You definitely see the linear equations if you augment it. Okay.
Yeah, but again, as you say, it's kind of useless, and I guess in an exam maybe you don't want to bother writing a row of zeros. I would. I'd write the zeros.
should at least work.
That's all right, we'll just roll. We'll do it next time.
Where was he?
I don't know where I put the black cloth.
I'm holding it.
Oh, easy. Thank you. Right. Another question. Show that something is a subspace. I believe this is a 3-mark question. You should be prepared for a subspace question on your class test. I haven't seen your class test, but I'm pretty sure that you'll find a subspace theorem question on there. In order to show something is a subspace, you need to do 3 things. You need to, first of all, show that 0 is in S. This is the first thing. Subspaces must contain the 0 vector. Good, so you're going to start proving that something is a subspace by saying 0 is in S because, and there's going to be some reason for this which will depend on what S looks like. So here we have some set of vectors from R3 that satisfies these conditions. We'll see that the 0 vector from R3 satisfies these conditions. Because, let's say 0, which is equal to 0, 0, 0, is an element of R3, and, well, when I plug the first component in, I get 7 times 0, and 4, oh sorry, these 3 things are what it means to be an element of S. You're a vector in R3, check. You satisfy this condition, check. You satisfy this condition, check. 0 is an S. All right, let's do the next condition. So this is item 2. You may recognize this. If x and y are vectors from S, we must show the sum is in S. You have to use the fact that the vectors come from S. If you're not using the fact that the vectors come from S, you're doing it wrong. There's something about the properties of S which will make this work. So please always start with that x and y come from S, and then the second thing you should do is just unpack what that means. So that means if x is in S, then that means this first condition holds. It's a vector from R3, 7x1. It also, so that's just, this is just unpacking what it means for x to be in S. Again, unpacking what it means for y to be in S. I'm going to need this stuff. This is the only hope I have of actually proving that x plus y is in S. Good, so this is my machinery, and now I need to wield it and prove that x plus y is in S. And x plus y then x plus y, which is this, is in S because, well, it's a vector in R3 and 7 times the first component plus is equal to, well, I can group my x's and y's together. That's 7x1 plus which is equal to 0. That's 0 by this condition up here. That bit's 0 by this condition up here. Therefore, this thing is 0. So it's quite critical that I had these pieces of information handy because I need them to be able to show this condition applies or is satisfied for x plus y. And the second condition is that the second component well, again, I'm just going to group these together with the x's and the y's and then use these conditions up here. So x. That's a y. y2 minus 3y3, which is equal to 0. Again, because that is 0 and I know that is 0. And that's all you need to do to show that x plus y is an element of S. It's an element of S because it's a vector in R3 and it satisfies that condition and that condition. Good. I'm 2/3 of the way there to proving that the subspace theorem holds, to invoking the subspace theorem. And the final thing I need to do is prove it's closed under scalar multiplication. Three. Again, I need to start with a vector in S. This can't be some random vector you pulled off the street. It has to belong to S. And loyal lambda can be any lambda you pull off the street, but you have to have a vector from S. And you have to conclude that lambda x is also in S. But the only way we're going to be able to do that is using some of the properties of S that we know x has. So let's just unpack what it means for x to be in S. Well, x can be equal to x1, x2, x3, which is a vector in R3. It satisfies these conditions. 7x1. Good. Now I'm just going to boldly claim that lambda x is in S. I mean, I know this is true. The question tells me that it's true. It must be true, and now I'm going to give you some reasons why. Lambda x is equal to lambda, which is a vector from R3, and so it's a vector from R3, and it satisfies these conditions. Well, now I need to use this information to prove that this is 0, and that's pretty straightforward because I can just factor out the lambda. And so that's this condition satisfied. I just need to show that this condition is satisfied. Lambda x2 so my second component minus 4 times my third component is just lambda, which is lambda times 0, which is again equal to 0. So we proved that it contains 0, it's closed under addition, and it's closed under scalar multiplication, hence can tie all that up in a neat little bow and say by the subspace theorem, this is a subspace. You should only be thinking subspace theorem. Anytime you see the word subspace in a question, you should just go straight to the subspace theorem. That is how you prove something is a subspace. Josh.
So yeah, I mean, these proofs, the logic is fairly standard. Once you understand one of these proofs, I think you can usually use the logic to do any of these questions. I guess one change I might personally make when I'm writing this out is just whenever I've proven one of these facts, I like to state the name of the fact I just proved. So here we prove that S is closed under multiplication by scalars. So usually once I've done that, I will just state what it was I was doing. So I would put here, hence S is closed under multiplication by scalars. I think that shows the people you know what you're talking about. But this does show it is closed under multiplication by scalars, so you have done all three. Yeah, I guess that's the only change I would make. Yeah. And I also think this is a very important statement, the one at the end, saying that you were using the subspace theorem. If you just prove these three facts, you didn't tell me why you were proving these three facts. I feel it's a little bit deficient as a proof. You should be saying, and this tool carries me the rest of the way to proving it is actually a vector space, a vector subspace.
There's actually quite a bit in here to only give 3 marks to, because there's so many things that we talk about.
Yes.
But for a 3-mark question, I think 1 mark for each of these things. That one's probably a bit easier than the other two. 1 mark each for closure under addition, closure under scalar multiplication.
I did like how you were pointing out there actually are 3 conditions here. There is the fact that it must be in a vector from R3 and satisfy these 2 conditions. So it's really 3 conditions defining this set.
That's more my literal kind of interpretation of what was written. Must be 3 things.
Okay.
Yeah, good. All yours.
Apparently we're getting quite close to the top boundary.
Oh, okay.
We'll bring things down.
We'll give it some margin then. All right.
Alright, so this is actually another 3-mark question. There are 3 parts, so I guess 1 mark for each part. Again, like all the questions we've been talking about, there have to be reasons, you have to be explaining yourself. This is a true-false question, but true-false with reasons. So we just want to look at these statements, decide whether they're true or false, and give a reason why it's true or false. So the first one is a set of 5 vectors in R5 must be a basis for R5. So the key word here is must. So if you think about it, this statement would be claiming that no matter how badly you choose these 5 vectors, they must form a basis. And to be honest, I can make quite bad choices, so I think this is false, and I can show it's false. So part I, well, it's false. Not every set of 5 vectors is a basis, because you could just choose 5 which are linearly dependent, and then they can't be a linearly independent spanning set or basis. So let's just give an example which fails. So false, since, well, let's take the following set. Say the set of vectors 0, 0, 0, 0, 0. That's already a pretty bad choice. Vector 1, 0, 0, 0, 0. Let's say 2, 0, 0, 0, 0. So my choices are horrible because I'm not even trying to do anything with the other 4 components. I'm just playing around with the first component. And 4, 0, 0, 0, 0. So this is a set of 5 vectors in R5, and clearly it's not a basis. I mean, I can't make any element which has a 0 off the first component. And I might just give a, so it's not a basis and clearly linearly dependent. I guess that's clear because there is a zero vector in there. Any set with a zero vector is linearly dependent. So that's false. What about part 2? A set of 6 vectors in R5 cannot be a basis. So it's not possible to make a nice choice and get a basis for R5. And in this case, again, this is false. Because no matter how smart I am, I can't make this work. A set of 6 vectors in a 5-dimensional space must be linearly dependent and therefore can't be a basis. So I'll say false. So since the dimension of R5 is equal to 5, let's see, so since the dimension of R5 is equal to 5, any set of 6 vectors from R5 must be linearly dependent. Well, a basis is a linearly independent spanning set, so that can't work. Sorry, dependent. And hence, oh wait, did I say false? No, sorry, this is true. So I'm agreeing with this statement. This statement is a true statement. So this is true because it just can't be done. So yes, it must be linearly dependent and hence not a basis. And so the important fact here is 6 is greater than 5. And what about this last one? This last one says, that a set of 7 vectors must be a spanning set for R5. This is actually fairly similar to the first one, actually. It's saying that no matter how poorly you choose these 7 vectors, you're always guaranteed to get a spanning set. Again, I know I can make terrible choices, so I know this is false. So part 3, this is false. So again, I probably can just give a reason. So I can just give an example where it doesn't work, where I don't get a spanning set. So false since, well, that example is almost an example I want. Let's just write down sets similar to that one. So 6 vectors which clearly don't form a spanning set.
Just take like E1, E2, oh sorry, E1, 1E1, 2E1.
Yeah, that's what I was thinking. So let's take the vector E1, the first standard basis vector. Let's double that. Let's triple that. Let's take 4 times that. Oops, that was E2. And I guess I can use a shorthand, so it's 1 up to 7. E1. So 7 different multiples of the vector E1 is not a spanning set. And if you want to be a bit more verbose, you can just give a little bit more of a reason, since we cannot make, well, let's give an example. We cannot make the vector E2 from these. You can't make any vector which has a non-zero component in the second place, so I think that's a good reason. And yeah, this shorthand for the standard basis vectors is probably quite helpful. I could have used it up here actually, but I want to be a bit more explicit just to show these off. So we have a false, a true, a false, and the important part is we gave reasons, and the reasons are worth the mark, the true or false. It's important, but the reasons are going to get you the marks.
No, absolutely. I think just saying false and giving a kind of crummy reason is not going to be enough. So when I'm reading these, I'm actually looking for examples of 5 vectors which, in this case, are not a basis. This is true, but it's probably a bit overkill for what we've what we've been asked, because a basis can only have 5 vectors in it. So this could have been a lot faster. And this shows a lot of understanding of the course. But
Yes.
5 vectors is to be a basis, you have to have exactly 5 vectors.
Yes, actually that's true. That's pretty much the definition of dimension. Dimension is the number of vectors you need to make a basis. So if I take 6, not matching the dimension, yeah, of course that's broken. So yeah, I probably should have thought of that.
But this is the reason why it's broken. But you can just say 5 vectors. You have to have 5 vectors in the basis.
I guess
Cool.
yeah, every basis for R5 contains 5 vectors. That's an important point. Okay,
Next question. Let's do it. Okay, here we have some vector from R4 and some matrix. Is B in the column space of A? And maybe I just want to spend a little bit of time unpacking what it means. The word column space of A, what that actually means. Also it says give reasons, so you can't, without this, theoretically you could just say yes or no, and that would be a 50% chance of getting the right answer and getting full marks. But it says give reasons, so just saying yes or no doesn't actually get you anywhere. What really gets you the marks here are the reasons. So, the column space of A. The column space of A is the span of the columns of A. So an equivalent question would be, is B in the span This is an equivalent question. You don't need to write this in your exam, but you may see in your exam a question like this, and really this one or anything about is something in a span gets solved in the same way, where you throw with row reduction. So maybe even you get a B1, B2, B3, B4, and you have to see conditions on that B to find whether or not it's in the span. It's always throw it in a matrix, row reduce. And that's exactly what we're going to do here. So we're just going to solve and I'm just going to spend a moment to heed Josh's good advice and check that what I'm writing is actually what the question asked me. Good, I think that's all right. And now I row reduce. So this should just be muscle memory at this stage. Uh, 0, 7 minus 8 is minus 1. Negative 6 plus 2 is minus 4. Please don't stop here, by the way. Some of you may be able to foresee that this is not going to have solutions. You need to go all the way to row echelon form before you start making such bold claims. So you may be able to predict that this is not going to have any solutions. Row echelon form first before you start making predictions like that. here I'm doing 2 row operations. I normally don't recommend you do 2 row operations at once, but because this is just going to give me a row of zeros, I'm going to make an exception. Good, this is row echelon form. Say these are my leading terms, and I'll notice that this column here is a leading term, which means there are no solutions. And now I'll reinterpret this back into the question I was given, hence B is not an element of the column space of A. Good. Josh.
So I think, was this only a 2-mark question?
I'd say so.
Yeah, there's, yeah, I mean, should be fairly straightforward. You have a simple check to do. You need to know there are some solutions. And yes, I do agree, you need to reach row echelon form. Yeah, stopping here and saying, no, I don't feel convinced. I don't feel like you've really shown me why it's not working.
Also, there's a kind of burden of arithmetic that must be done here, and someone who stops here hasn't kind of passed enough of the loop of the hoops as someone who's passed through here. The marks are partially awarded on accuracy for a question like this. You need to be able to accurately perform the row operations, and so if you just stop here, then you kind of just stopping too soon. You haven't shown us enough mastery of arithmetic yet.
Yep, yeah, fairly clear. And yep, no solutions and conclusion. Always good to have a conclusion.
But any question about column spaces or is something in the span of other things as it's been written here will involve you doing something like this. We just throw it into a matrix. Even if you don't understand entirely what the question's asking you, throw it into a matrix, do the row reduction. You're probably going to get most of the marks just from doing that correctly.
Right. Okay. Yeah, I feel like there's not much else to say.
Right, let's go to the next question.
Okay, so we have the following question. We're given a function from R to R, and this is actually as a vector space R, so it's very uncommon to see this, but R is a vector space over the field R, which gets confusing. But we have this function and we want to show that it is not a linear transformation. So something must be broken. It's either going to be the addition condition, or it's going to be the scalar multiplication condition. In this case, I suspect it's actually both. I'm going to try and do this one by using the addition condition. Just show that for 2 particular values, if I take, say, t of x1 plus t of x2, it's not the sum of those 2, but a bit more clear than that. We just need one little example where it's broken. So let's see. So let's consider, well, since we have this cosine, let's pick values that make our life easy. Let's consider what happens when we plug in pi over 4 into this map. So t of pi over 4 is pi over 4 times the cosine of pi over 4. Cosine of pi over 4, so cosine of 45 degrees is 1 on root 2. So this will spit out the number pi over 4 root 2. Yeah. Okay, and actually that's the only value I really need to know. So let's now consider let's consider what happens if we take the map and apply it to pi over 4 plus pi over 4, which is to say we apply the map to pi over 2. Well, if we do that, we get pi over 2 times the cosine of pi over 2. Cosine of pi over 2, that's nice, that's 0. So this actually spits out the number 0. And note that this is not equal to what happens when you take the map applied to pi over 4 plus pi over 4, and this quantity here is pi over 2 root 2, not 0. So if this were a linear map, the addition condition says that these must be equal, but they're not equal. So I will just say hence t does not satisfy the addition condition. So that means it can't be a linear map. So hence t is not a linear map. Right, now I believe this was a 2-mark question. Was it 1 mark?
I'd say 2. Yeah, there's some work to be done here. You need to pick your kind of values carefully, and you need to know what to do. So I guess 1 mark for kind of knowing what condition you're going to use. Sometimes the maps will be, say, closed under scalar multiplication, but they won't be closed under addition. So you'll need to kind of know which one of those to do. Trial and error is probably the best way to go here. Sometimes for unfortunate values of your input, you will actually discover that t of, say, the sum of the two things is twice t of the one of those things.
Yes, yeah. I must admit, I had thought ahead when I chose this. I was thinking I would love this to be a 0, and I know how to do that. Just pick pi over 2.
Mm-hmm.
So I want to take half of that. Take pi over 4.
Yeah. So I think there's some that cleverness is worth some marks,
Yes.
or some foresight, shall we say?
Yeah, I think, and this question, I especially want to see an example of how it breaks. Don't do it using general numbers. Like, don't unspecify x and y. Just show me for some numbers that it's just broken.
Yes.
I think the technical two terms are the addition condition and the scalar multiplication condition. It's very common, and actually Daniel just did this, to say closed under addition. That doesn't really make sense in this context. We're not talking about the subspace. It's supposed to be the addition condition. That's, yeah. Okay. So yeah, for this one, I think you need to be just a little bit clever. And if it doesn't work, start again. We've told you it's not a linear transformation, so you know what you're doing. You just need to find a nice example. I could have also done this using, pretty close to this example, take t of this and t of twice this, and you get, again, doesn't work. Many ways to show it's broken. Okay.
Cool. Next one. Last one. Awesome. There we go. So you have some function t. You're not told if it's linear. It just maps R2 to R3, and you're told what it does to these things. Show that it cannot possibly be linear. Okay, so the first thing you're going to have to do with these questions is express one of these things as a linear combination of the others, and in this case it's particularly easy to do that. Since you may have to work a little bit harder to obtain a relation like this, but they've been very kind of kind to us in this case. The vector 5, negative 1 is just a linear combination of the other two. Then t of 5, negative 1 is t applied to whatever this stuff is, because t, well, it's the same input, so it should give us the same output. Now we suppose what happens if t were linear. If t is a linear transformation, then t applied to this sum is just t applied to, well, I'll just write it down instead of speaking it. That's equal to just using the fact that we're supposing for a contradiction that t is linear, in which case this becomes t applied to the sum of these things individually, so it's t applied to 5 times that vector plus t applied to that vector, and I can bring the scalars out, so you can just straight up write it down like this. And I know what t does to 0, 1, and I know what t does to 1, 0, and I know what t does to 0, 1. This just gives me 5 times this thing, minus whatever t did to 0, 1, which is equal to 5 minus 2, 5 minus 3, negative 5 minus 2. So if t is a linear map, then this is what 5 of t negative 1 should be, but that's not what they told us. A contradiction, hence t cannot be linear. Josh?
Yeah. So you can see this is actually very similar to what we just did for the last question, although here they actually give you the starting values. I had to find my own for the other question. So they don't tell you explicitly what the map is, they just give you these 3 pieces of information, and you're just supposed to show the contradiction. Yeah, I think this is fairly nice, fairly short. I guess this would also be worth about 2 marks.
I'd say 2 marks, yes. I'm not sure where exactly. Maybe 1 for kind of using the linearity condition correctly, and 1 for doing the arithmetic.
1 in this area, and then
yeah,
possibly another 1 for actually getting the contradiction right.
This could easily be a 3-mark question if this relation is difficult to obtain.
Yes, that's true. Yeah, I think it's a fine solution. It should be worth full marks if you do
Awesome.
the test.
Awesome.
And that was actually the last question we had prepared for this stream.
Cool. Well,
So-
thank you for joining us. I have to point out something about the matrix representation theorem. It will not be on your test. So there's some class tests in the book that have the matrix representation in it, theorem in it. You do not have to worry about that for this class test.
So maybe the next one.
Yeah.
Right,
Cool.
well,
All right. Thank you for joining us.
Thank you for joining us, and good luck on your test.